Hello and welcome to the Bored to Sleep podcast. We aim to talk about topics today so mundane that you fall asleep. Each podcast will be roughly 20 minutes. During the final 5 minutes, we will gently fade out, allowing you to fall asleep. So relax and we will begin. Today's topic is cement, read from Wikipedia. A cement is a binder, a substance used for construction that sets, hardens, and adheres to other materials to bind them together. There are two main forms of cement: geopolymer cement and Portland cement. Cement is seldom used on its own, but rather to bind sand and gravel together. Cement mixed with fine aggregate produces mortar for masonry, or with sand and gravel produces concrete. Cement is the most widely used material in existence and is only behind water as the planet's most consumed resource. Cements used in construction are usually inorganic, often lime or calcium silicate based, and can be characterized as either hydraulic or non-hydraulic, depending on the ability of the cement to set in the presence of water. Non-hydraulic cement does not set in wet conditions or underwater. Rather, it sets as it dries and reacts with carbon dioxide in the air. It is resistant to attacks by chemicals after setting. Hydraulic cements, e.g. Portland cement, set and become adhesive due to a chemical reaction between the dry ingredients and water. The chemical reaction results in mineral hydrates that are not very water-soluble and so are quite durable in water and safe from chemical attack. This allows setting in wet conditions or underwater and further protects the harder material from chemical attack. The chemical process for hydraulic cement was found by the ancient Romans. They used volcanic ash and added lime, calcium oxide. The word cement can be traced back to the Roman term opus caementicium, used to describe masonry resembling modern concrete that was made from crushed rock with burnt lime as binder. The volcanic ash and pulverized brick supplements that were added to the burnt lime to obtain a hydraulic binder were later referred to as cementum, caementum, carmentum, and cement. In modern times, organic polymers are sometimes used as cements in concrete. Perhaps the earliest known occurrence of cement is from 12 million years ago. A deposit of cement was formed after an occurrence of oil shale located adjacent to a bed of limestone burned due to natural causes. These ancient deposits were investigated in the 1960s and 1970s. Cement, chemically speaking, is a product that includes lime as the primary curing ingredient, but is far from the first material used for cementation. The Babylonians and Assyrians used bitumen to bind together burnt brick or alabaster slabs. In Egypt, stone blocks were cemented together with a mortar made of sand and roughly burnt gypsum, which often contained calcium carbonate. Lime, calcium oxide, was used on Crete and by the ancient Greeks. There is evidence that the Minoans of Crete used crushed potsherds as an artificial pozzolan for hydraulic cement. Nobody knows who first discovered that a combination of hydrated, non-hydraulic lime and a pozzolan produces a hydraulic mixture, but such concrete was used by the ancient Macedonians and 3 centuries later on a larger scale by Roman engineers. The Greeks used volcanic tuff from the island of Thera as their pozzolan, and the Romans used crushed volcanic ash with lime. This mixture could set underwater, increasing its resistance. The material was called pozzalana, from the town of Pozzuoli, west of Naples, where volcanic ash was extracted. In the absence of pozzolanic ash, the Romans used powdered brick or pottery as a substitute, and they may have used crushed tiles for this purpose before discovering natural sources near Rome. Pantheon in Rome and the massive baths of Caracalla are examples of ancient structures made from these concretes, many of which still stand. The vast system of Roman aqueducts also made extensive use of hydraulic cement. Roman concrete was rarely used on the outside of buildings. The normal technique was to use brick-facing materials as the formwork for an infill of mortar mixed with an aggregate of broken pieces of stone, brick, potsherds, recycled chunks of concrete, or other building rubble. Any preservation of this knowledge in literature from the Middle Ages is unknown, but medieval masons and some military engineers actively used hydraulic cement in structures such as canals, fortresses, harbours, and shipbuilding facilities. A mixture of lime mortar and aggregate with brick or stone facing material was used in the Eastern Roman Empire, as well as in the West into the Gothic period. The German Rhineland continued to use hydraulic mortar throughout the Middle Ages, having local pozzolana deposits called trass. Tabby is a building material made from oyster shell lime, sand, and whole oyster shells to form a concrete. The Spanish introduced it to the Americas in the 16th century. The technical knowledge for making hydraulic cement was formalized by French and British engineers in the 18th century. John Smeaton made an important contribution to the development of cements while planning the construction of the third Eddystone Lighthouse in the English Channel, now known as Smeaton's Tower. He needed a hydraulic mortar that would set and develop some strength in the 12-hour period between successive high tides. He performed experiments with combinations of different limestones and additives, including trass and pozzolanas, and did extensive market research on the available hydraulic limes, visiting their production sites, and noted that the hydraulicity of the lime was directly related to the clay content of the limestone used to make it. Smeaton was a civil engineer by profession and took the idea no further. In the South Atlantic seaboard of the United States, tabby, relying on the oyster shell middens of earlier Native American populations, was used in house construction from the 1730s to the 1860s. In Britain particularly, good quality building stone became ever more expensive during a period of rapid growth, and it became a common practice to construct prestige buildings from the new industrial bricks, and to finish them with stucco, to imitate stone. Hydraulic limes were favoured for this, but the need for a fast set time encouraged the development of new cements. Most famous was Parker's Roman cement. This was developed by James Parker in the 1780s, and finally patented in 1796. It was in fact nothing like material used by the Romans, but was a natural cement, made by burning septaria, nodules that are found in certain clay deposits and that contain both clay minerals and calcium carbonate. The burnt nodules were ground to a fine powder. This product made into a mortar with sand set in 5 to 15 minutes. The success of Roman cement led other manufacturers to develop rival products by burning artificial hydraulic lime cements of clay and chalk. Roman cement quickly became popular, but was largely replaced by Portland cement in the 1850s. Apparently unaware of Smeaton's work, the same principle was identified by Frenchman Louis Ficat in the first decade of the 19th century. Ficat went on to devise a method of combining chalk and clay into an intimate mixture. and burning this produced an artificial cement in 1870. In Russia, Igor Cheliv created a new binder by mixing lime and clay. His results were published in 1822 in his book A Treatise on the Art to Prepare a Good Mortar, published in St. Petersburg. A few years later, in 1825, he published another book, which described various methods of making cement and concrete, and the benefits of the cement in the construction of buildings and embankments. Portland cement, the most common type of cement in general use around the world as a basic ingredient of concrete, mortar, stucco, and non-specialty grout, was developed in England in the mid-19th century, and usually originates from limestone. James Frost produced what he called British cement in a similar manner around the same time, but did not obtain a patent until 1822. In 1824, Joseph Aspdin patented a similar material, which he called Portland cement, because the render made from it was in colour similar to the prestigious Portland stone quarried on the Isle of Portland, Dorset, England. However, Aspdin cement was nothing like modern Portland cement, but was a first step in its development, called a proto-Portland cement. Joseph Aspdin's son, William Aspdin, had left his father's company and in his cement manufacturing apparently accidentally produced calcium silicates in the 1840s, a middle step in the development of Portland cement. William Aspdin's innovation was counterintuitive for manufacturers of artificial cements, because they required more lime in the mix, a problem for his father, a much higher kiln temperature and therefore more fuel, and the resulting clinker was very hard and rapidly wore down the milestones, which were the only available grinding technology of the time. Manufacturing costs were therefore considerably higher, but the product set reasonably slowly and developed strength quickly, thus opening up a market for use in concrete. The use of concrete in construction grew rapidly from 1850 onwards, and was soon the dominant use for cements. Thus Portland cement began its predominant role. Isaac Charles Johnson further refined the production of Massey Portland cement, middle stage of development, and claimed he was the real father of Portland cement. Setting time and early strength are important characteristics of cement. Hydraulic limes, natural cements, and artificial cements all rely on their baryte content for strength development. Baryte develops strength slowly because they were burned at temperatures below 1250 degrees Celsius, 2280 degrees Fahrenheit. They contain no alite, which is responsible for early strength in modern cements. The first cement to consistently contain alite was made by William Aspdin in early 1840s. This was what we call today modern Portland cement. Because of the air of mystery with which William Aspdin surrounded his product, others, for example Vicat and Johnson, have claimed precedence in this invention. But recent analysis of both his concrete and raw cement have shown that William Aspdin's product, made at Northfleet, Kent, was a true alite-based cement. However, Aspdin's methods were rule of thumb. Vicat is responsible for establishing the chemical basis of these cements, and Johnson established the importance of sintering the mix in the kiln. In the US, the first large-scale use of cement was Rosendale cement, a natural cement mined from a massive deposit of large dolomite discovered in the early 19th century near Rosendale, New York. Rosendale cement was extremely popular for the foundation of buildings. For example, the Statue of Liberty, Capitol Building, Brooklyn Bridge, and lining water pipes. Sorel cement was patented in 1867 by Frenchman Stanislas Sorel. It was stronger than Portland cement, but its poor water resistance and corrosive qualities limited its use in building construction. The next development in the manufacture of Portland cement was the introduction of the rotary kiln, which produced a stronger, more homogeneous mixture and facilitated a continuous manufacturing process. Calcium aluminate cements were patented in 1908 in France by Jules Bede for better resistance to sulfates. In the US, after World War I, the long curing time of at least a month for Rosendale cement made it unpopular for constructing highways and bridges, and many states and construction firms turned to Portland cement. Because of the switch to Portland cement, by the end of the 1920s, only one of the 15 Rosendale cement companies had survived. But in the early 1930s, builders discovered that while Portland cement set faster, it was not as durable, especially for highways, to the point that some states stopped building highways and roads with cement. Bertrand H. Waite, an engineer whose company had helped construct the New York City's Catskill Aqueduct, was impressed with the durability of Rosendale cement and came up with a blend of both Rosendale and Portland cement that had the good attributes of both. It was highly durable and had a much faster setting time. Waite convinced the New York Commissioner of Highways to construct an experimental section of highway near New Paltz, New York. Using 1 sack of Rosendale to 6 sacks of Portland cement, it was a success, and for decades the Rosendale-Portland cement blend was used in highway and bridge construction. Cementitious materials are used as nuclear waste immobilizing matrix for more than half-century. Technologies of waste cementation have been developed and deployed at industrial scale in many countries. Cementitious waste forms require a careful selection and design process adapted to each specific type of waste to satisfy the strict waste acceptance criteria for long-term storage and disposal. Modern hydraulic development began in the start of the Industrial Revolution around 1800, driven by 3 main needs. Hydraulic cement render, stucco, for finishing brick buildings in wet climates. Hydraulic mortars for masonry construction of harbour works in contact with seawater. Development of strong concretes. Modern cements are often Portland cement or Portland cement blends, but industry also uses other cements. Portland cement is by far the most common type of cement in general use around the world. This cement is made by heating limestone, calcium carbonate, with other materials such as clay to 1450 degrees Celsius, 2640 degrees Fahrenheit, in a kiln. In a process known as calcination that liberates a molecule of carbon dioxide from the calcium carbonate to form calcium oxide, or quicklime, which then chemically combines with the other material in the mix to form calcium silicates and other cementitious compounds. The resulting hard substance called clinker is then ground with a small amount of gypsum into a powder to make ordinary Portland cement. The most commonly used cement, often referred to as OPC. Portland cement is a basic ingredient of concrete, mortar, and most notably, grout. The most common use of Portland cement is to make concrete. Concrete is a composite material made